see you. So good to see you. So I want to say thank you. My name is Christopher Sleeper. I am the coordinator of the honors program, and this is the second session of 3 sessions for our OMNI, and so I want to welcome all of you to our fall OMNI. The fall OMNI really came about many, many years ago. It was part of a conversation that I had with a faculty member who has passed on. And he was hoping, his name was Rob Archer, and he was in the humanities department. And he always just loved this opportunity for students to get together at the end of the semester and share what they had learned. And he had done it in different settings, and sometimes it was over food, sometimes it was just in person. But the idea was to exchange knowledge and to nurture that exchange of knowledge, because so much of what we do is in the beauty of our classroom. And was it appropriate? Absolutely. To then come outside and then share it with others and continue that process of learning. And so in the spirit of Rob Archer, we continue to honor his gift to our college, his teaching, and his long years of service by doing the OMNI. And so the OMNI came about in 2017. And we created an honors contract system that year, and it was a way for, even when students were working individually with their professor, for them, you have a larger setting that you could share your work in and continue. And it just so happened that there were some transfer benefits as well, that while thousands of students take honors classes every single year, less than 1,000 students will end up presenting in a research conference. So it was a great way for students that were thinking about going into, to transfer, for them to kind of have some ways to build up their resume that might not be duplicated by other students. And so it was a great kind of opportunity for students to work closer with their professors, to build up their resume, to kind of work with others and connect with others. I am still networking with students that I met in the OMNI in the spring, and I saw them at UCLA last Friday, and it's just awesome. The journey continues. And so I am so grateful that we have this OMNI, and I want to thank you for working even here at the end of a semester so hard to put these presentations. The OMNI is meant to be a student's often first-time research experience. And so what I want you to understand is that this is a collection of friends, sharing in your success, but also wanting to learn from you. And we start with this kind of idea that we're all doing something that's challenging just by being here today and sharing that time and making ourselves sometimes uncomfortable, but it's a good type of uncomfortable. It'll help you in your future academic and professional success. So I want to, again, kind of set some ground rules of being supportive, be present, put those cell phones away and totally engage in that time that we have today. And so before we begin our poster presentation, I want to, again, say thank you. I want to thank Elizabeth. We could not have an honors OMNI without her, and so can we give her a round of applause? She puts together the program, she puts together sessions and panels and works with me. I'm a visionary type. I am not so great at nuts and bolts, and it just so happens I have the best craftsmen to work with, and so that's Elizabeth, so I just want to say thank you for that. I also want to thank our administrators. Right behind here is some of the most incredible administrators and staff. Susan Corley, for instance, who kind of handles our budget for the program. Danae Pescarona is the VP of Instruction. So on your way out, if you want to just kind of walk through this building right here and just say thank you, I would love that. And for faculty members, I just want to say thank you as well. Because we couldn't have an honors program, we couldn't have a contract system without your work. Writing the courses, they do this on a volunteer basis. They don't have to do honors contracts or honors classes or engage, but they do this because they want to engage with you. So we have faculty members here, and we have a special pin for you if you haven't gotten it that says Honors Mentor, OMNI Mentor, and so wear it proudly. But can we give them a round of applause for being here today? And for our students, we couldn't also have an OMNI without you. It's kind of this beautiful agreement that the faculty come in and want to engage with this, but then we also have students who want to engage with this as well. And so our students come in different ways and forms. Some are just to support and be moderators today. And so we have great moderators like Shiva here, but then we also have navigators that are also providing as hosts moderating duties. And I really believe in a student-centered program where student leadership basically carries us forward inside and outside the classroom. And so moderators like Shiva and navigators like Marilyn and Olivia are just so crucial for our program, and we're so thankful for their contributions. Can we give them also a round of applause? We went to UCLA last Friday. We brought 36 students there. Couldn't have done it without Olivia and Marilyn. So it's just part of what we do here as a program. And again, I want to finish with the most important group, which are our student presenters. It's hard last week of the semester doing an extra assignment, right? And getting presentations ready. Whether you're doing posters or oral presentations today, I just want to say thank you for putting in that hard work, for probably staying up late last night and other days over the last few weeks just to do this. It's special, and it marks you, as I said, different than so many of our students in our program, but even around the state. And so I am just so grateful for this opportunity to learn from you today. That's one of the things I look forward to the most, is that as a coordinator, but also as a history professor, I get to learn so much from others through this wonderful two-day OMNI. So at this time, I'm going to turn it over to my moderators, who are going to kind of open us up into, I guess we're going to just go into our poster session, right? We're just going to go straight into that. So at this time, we have 3 poster presentations, and normally we used to go into OMNIs that had like 50 or so posters here. We're a little smaller now, but we're mighty. We're mighty. But the good news is that all of us get to spend time with you. So there's still some foods out there, but if you would like to now kind of rise up, get some blood moving, and participate in a time-honored tradition of, again, learning from our different presenters, what I would like you to do is kind of make sure you visit all 3, but just have this opportunity to learn from these different students. So at this time, are you all ready? We're all okay. So come up and learn, and then I'll bring us back for our next part of our session. Thank you.
So we can be beginning with Kevin Hu and Professor Giga Pervich analyzing and interpreting Keisha's rendering equation and its applications, defining the components of rendering equations and explaining its applications and identifying its limitations.
Alright, hopefully you guys can hear me just fine. Hi, my name is Kevin Hu, and as you heard, I'll be talking about the rendering equation. This is especially important in things like modern CGI, where we have to render things on a computer efficiently and fast. Can we go to the next slide? This is just an introduction of what's to come. So I'm going to start by giving you guys the big idea of what is rendering and what the goals are when it comes to rendering. And then I'll help you follow through sort of the rendering equation and how we actually apply that when we do ray tracing within rendering. Can we go to the next slide? So what is the big idea? So in order to understand the rest of my presentation, I want to give you a big idea of what our goal is. So the way that we produce images in the real world, especially with cameras, we usually have a film within our camera that we allow to capture rays of light, usually from sunlight source. When you're outdoors, it's usually the sun. And when we see things like trees, it's usually because the light from the sun reflects off these trees onto the film of the camera. And if you've ever taken a picture, you know there's this thing called exposure. So with more time, the more light you capture, the more detailed of a picture you get. So our goal with rendering is sort of to simulate or emulate this on our computers. We want to emulate this digital camera here, and in order to do that, we usually have objects defined ahead of time, 3D objects, and we'll usually give them some coordinates in space. We'll define them in a file. And then what we'll do is our goal is to project these 3D objects onto some viewing planes, which is in 2D. Now, immediately, one of the biggest problems we have is because we're projecting it onto this 2D plane, we lose a dimension, a tangible dimension, which is depth. Because once you put it on the screen, it's kind of hard to figure out how deep an object is. And can we go to the next slide? And that's why light is important. So here, we can see it sort of rendering without light. Another immediate challenge that I want to talk about is also I want to give you an idea of the sheer amount of calculation we have to do with computers. So this is the image of, let's say we have spheres in the space, and they're all different colors. When you only have 256 pixels, which is small squares put next to each other, and then you give each one a color in order to identify objects in the space, you get a really jumbled image that doesn't really give you much information about the scene. But even with more pixels, like 1 million pixels, we can tell that there are circles, but there's no way to differentiate them as spheres. So if we go to the next slide. So this is what happens when we now put light on it. When we look at it now, we can tell that there's depth because there's light and they produce shadows. And that is sort of the goal that I'm going to talk about of rendering, is how we use ray tracing to sort of emulate light in a 3D scene. So now I'm going to come back to this image. What is ray tracing? Well, the way we intuitively understand cameras when we produce images on a film on camera is we have rays come from a light source, like the sun or a lamp, and it bounces around the scene, and eventually it will hit the camera film, and with time, you develop the film and you get an image. If you ever taken a Polaroid photo, you usually have to like hold it, let some light come in, and then cut off the light, and then let the film develop. If you're going to go to the next slide. However, one of the problems about using this sort of logic when we're trying to emulate it digitally is there's a lot of waste. And what do I mean by waste? Well, if you look at this diagram here, you'll see that the light hits the tree and then it produces these rays. However, only one of these rays actually hit the film. The rest of the rays go past the film. And what this means is they don't actually contribute anything to the image. Now, while this works in the real world because we don't actually have to deal with the light because the light is organic, in a digital space, we have to find a way to emulate all these rays. And if we do it the intuitive way, a lot of these rays will be useless, and then we'll just have spent unnecessary time trying to calculate them. And so if you remember, with the 1 million pixels, if we cast 1 million rays into a space, and a lot of them miss the camera, we're not going to get that detailed of an image. So the solution that they came up with is, what if instead we cast rays from the camera? Now, this is where it gets a little confusing, but give me some time. I know if you're thinking, how can we possibly cast rays of light from the camera and produce an image? That doesn't really make sense. So the logic behind it is, I think a better way to frame it is that we're not casting rays of light from the camera, even though it is called ray casting. What we're technically doing is we're trying to identify the specific rays of light that will generate an image. Because if you remember from the diagram before, there are rays of light that don't hit our camera, therefore they don't produce an image. So I created a quick demo here to sort of just demonstrate a little bit how it works, and then we'll go into a little bit of the math part of it, and then we'll combine the two in order to see how it's used in real time. So one of the logic that we use intuitively is that if there's a light, then we can see the room, so we can see the image. So if there's the sun, then we can see what's around us. Using this logic, we can actually turn it around and say, well, if we know ahead of time that there must be an image that we're able to see, there must be a light in this room that produces this image for us. So if you want to go to the next. So if you remember the diagram from before, when there are a lot of rays coming from the camera, they're usually produced from a pixel. So we're just going to follow one of these pixels. So let's just say we have a pixel on this camera, and we're trying to figure out what color and how much light to put on this pixel in order to show to the user, right? So we follow this, or we have the camera cast a ray of light, or not a ray of light, or just a ray. And then we ask the object that this ray hits, which is the table. We ask if the table is emitting any light. And if the answer is yes, then the calculation is quite simple. We just give this value to the pixel and say that's how much light the camera sees from this ray. However, we're going to go to the next one. The answer is no. So because we know that the table doesn't emit any light, and keep in mind, we know that there must be an image that we're able to see, that means there must be a light somewhere else in the room. So instead, what we're going to do now is we're going to cast rays from this table in infinite directions. So if you imagine we have a camera, we hit the table, we're going to go in every direction to try to find a light somewhere. So let's just assume we follow one of the rays that actually do hit a light. Go to the next one. So now the table projects all these rays, but we're just going to assume we're going to follow this one ray, this isolated ray that hits the light. Next one. This time, we ask the same question. So essentially, you'll just keep doing this process and asking the same questions until you hit a light. So now that we've actually hit a light, therefore we know now that the light produces something, and then we also know that the camera will eventually have a ray that hits this light. So we've isolated one chain of rays of light that will actually produce an image that's not wasted and goes past the camera. So if you go to the next one. So we send this data back to the initial array, and then we create this chain of arrays. So we have R1 plus R2, and from this chain of arrays, we know that there's a light, it hits the table, and it should reflect some sort of brown light to the pixel, and then we can put this brown light on that one pixel for that one point on the table. And basically, we do this for every pixel in the scene until we get an idea of what the image in the scene looks like. So now let's talk about the actual math behind it. I know this looks terrifying. I was scared when I looked at it in the paper too, but it's actually not as terrifying when we simplify the parameters. If you want to go to the next slide. This also looks a little scary, I know, but if we actually put it into English, it actually makes quite some sense intuitively. So the point of this equation is to, in order to evaluate the amount of outgoing light, so that L sub O term, we just take the sum of the emitted light, so if it was like a lamp, emits some light, and the amount of reflected light. Which, if you think of it that way, it's not too complicated, because the emitted light, you can just tell ahead of time how intense this light is, just take the sum of that with the amount of reflected light. Now, the goal of my presentation here is to really break down this integral, what it really means. Because yes, it's the reflected light, but there's a lot of factors that come into play when we deal with reflected light. So go to the next slide. So there's 4 main ideas when it comes to this integral, and I'm going to help you break down each part of it. Next slide. So the actual integral itself, if any of you guys have taken a calculus class, you might be confused about the integral, because usually bounded integral has 2 limits. But this omega here is just saying that we're taking this hemisphere around the point, if you remember from before, where we had the table and then we cast rays over infinite directions. We're just trying to take into account all the incoming light and the amount of outgoing, the amount of reflected light going in an outgoing direction. So if you think about it, the amount of light that a surface that doesn't emit light projects out in one direction comes from the amount of reflected light from everywhere else around it. So that's essentially what this integral is saying. Now, this is where the biggest part of research for this equation comes in, because this is where we sort of emulate the actual material of the surface. Now, I'm not going to go into too much detail about this, because there's many different models, but I want to isolate 2 models just to give an idea of what the BRDF really does. So let's say you have 2 surfaces. You have some sort of like carpet surface like you see on the floor, or something that's metal. There's nothing in this room that's metal, but just like a mirror, or like your car. You know how the car is shiny? You say it's shiny, it's glossy, right? So there's 2 models here. We have Lambert's BRDF model and Vaughn's BRDF model. So Lambert's BRDF model just assumes that a surface diffuses light evenly, and so when you have a ray that hits a surface that applies Lambert's BRDF model, you can just assume that it diffuses light evenly, meaning that it'll have like a matte-looking surface. So as you can see, it looks smooth. Now, if you apply Vaughn's BRDF model to a surface, so you hit a surface, you say it's glossy, I want to apply Vaughn's BRDF model, you do some math, and you get this number that tells you basically that it should be shiny. And what does it mean to be shiny? Usually when something is shiny, you have a source of light, and it will hit the surface. And usually the part that gets hit directly by the light will usually have a little glow. So you can sort of tell where the light came from. Whereas for the Lambert's BRDF model, it's a little harder to tell because it's a lot more even. So next slide. And finally, we have the dot product. The dot product, if you don't really understand what a dot product is, all you need to know is that it's pretty much just a way to sort of take into account the angle at which the light hits the surface. Now, if you take your phone camera, your phone flashlight, and you point it directly at the table, you'll notice that it's really bright when you're putting it perpendicular to the table. But as you move it to the side, it'll start to diffuse out and have a little less intensity. That's basically what this dot product takes into factor. So if you move the light to the side, it's going to be less intense than if you shine it directly onto the ground. Okay, next slide. Now, this is where I want to start going into the actual application of this equation. So I've talked to you guys about why we use ray tracing. I talked to you about the math behind it. But how do we actually use these numbers to evaluate some sort of image or pixel, or color or light? So next slide. So if any of you guys are familiar with a digital screen, you would you know that usually you produce colors by using the RGB channels, which have some quantity between that like balances out each color to make a lot of colors that you can then put on your screen. Next slide. So if you remember the demo before, our goal was to identify a chain of rays that eventually do hit the camera. So here, let's say we found a chain of rays that eventually hit a light source. Now we want to trace it backwards. So from the light source, it produces some light, and they usually come through some number. They use 10, 10, 10 here, and if you're familiar with RGB, it's usually 255, 255, 255. But for the sake of this demo, it makes the constants a little easier to understand, so that's why it's 10, 10, 10. So it hits this door here, and the next thing we want to do is plug it into the integral. And if you remember the integral, we had that one BRDF constant, which takes into account this actual surface of the material. So we know this door probably reflects light. We don't know if it's shiny or not or something, but the BRDF encapsulates that. Then we also know it's blue. So RGB, if we want it to be blue, we want the blue channel to be more prominent, and that's what you see here. So when we start from 10, 10, 10, we get some dampening factors, because once you hit a surface, it doesn't emit as much light usually. Due to the conservation of energy, we know it shouldn't emit more light than what's coming at it. So these numbers are less than 1. But you can tell that the blue value is the largest. If you can't see it, this is the 0.9, and this is 0.2. You apply that, you multiply them with the 10, 10, 10 light, and then you get some value that shows that the light should be blue. And eventually, you hit multiple surfaces. You do the same thing with each point at each surface, and then it comes back to the camera to this one pixel that you originally casted the ray from in order to identify this chain of rays. And now you know that this pixel should be blue. And so you do this with every pixel, and eventually you'll get a clear image. One of the biggest problems in terms of the actual efficiency of this is, remember before when I said that we have to take efficiency into factor, especially when we're doing modern CGI for like video games or something, because we want it to be in real time. If it takes too long, and if it's too expensive, then we can't have all these expensive effects that look really nice. So we have to always strive for the most efficient way, even if it requires sacrificing some detail, because in the end, we're trying to make things as fast as possible without sacrificing too much detail. So one method that I would like to talk about is Monte Carlo integration for efficiency. If any of you guys have taken a calculus class, you remember doing Riemann sums in order to calculate the area under a curve. Essentially what that means is, if we want to approximate the area under the curve, we would take these rectangles and we would put them next to each other, and then it's easy to calculate the area of a rectangle. We just sum up all these rectangles, and then we'll get like an approximation of the area under the curve. You can think of these rectangles as sort of rays, because with more rectangles, as you make them smaller and smaller, you get a better idea of the area under the curve. However, there is one problem, or at least one way we can make this more efficiently. So if you remember in the demo that I talked about, when you hit a surface, you want to cast infinite rays. But how can you tell a computer to cast infinite rays, because that would take infinite resources? We can't. So we have to find a way to approximate it. So the way we do it on 2D, I'll explain how we do it in 3D later. But in 2D, you can sort of make random rectangles and do the Riemann sum on these random rectangles. However, you'll notice that if we take the average of all these rectangles, these 3 rectangles at the bottom don't really give us much information about the area under the curve. In fact, we don't even need to take these average, the area of the rectangles, of those smaller rectangles. Give me the next one. So instead what we can do is we can just redo the process, but just don't take any rectangles from this smaller part of the curve, because we know ahead of time that there's not going to be much contribution from those rectangles. So how does this apply to 3D? You want to go to the next slide? Well, usually we know ahead of time in our scene where the light sources are and where there's no light sources. So if you want to hit it again. We know that there's a lamp here. So we know we definitely want to take a lot of samples around this lamp because we know it's going to project an image. But this tunnel, we know ahead of time probably doesn't produce light. And so we can just tell rays to take more rays and get more information from the light than from the tunnel. And doing it this way, we can make it a lot more efficient, and that's the application of ray tracing, and that's pretty much it to my presentation.
So thank you so much for presenting. Now we will start our 5-minute Q&A section. So if you have a question, please make sure to project your voice so everyone can hear and so our speaker can hear.
Any questions? Yeah, go ahead.
This is kind of an interesting approach to computing graphics, but applications of graphics, at least I'm thinking of graphics cards, are also super, I guess what I'm trying to say is that the process of computing like a bunch of variables at the same time for graphics is also like useful for other things that also have lots of variables, like in crypto mining or in like weather simulations or something. Can this process be expanded beyond graphics?
This specific equation probably cannot be extended beyond graphics because it is derived from light, the physics of light. However, I think the process of recursively calculating things does take advantage of graphics cards, which usually have dedicated cores in order to do these multi-threaded processes, which means like you run multiple processes at the same time. And in that sense, yes, it does make it more efficient for other things. But this specific equation does apply only to rendering. Any other questions? Go ahead.
So, what I'm wondering, I've always kind of wondered this. Why is in RGB the colors used with light for computers? Why does it have green instead of yellow? Since traditionally the primary colors are blue, red, and yellow. Why is green there instead?
That's a good question, and I don't know the answer to it, unfortunately.
I'm gonna get to that.
Oh, did you?
Yeah, it's because red, green, and blue mix together to an additive versus subtractive color mixing. So when you're mixing paints, it's subtractive color mixing because the more colors you put in, the closer to black you get. With RGB, the more colors you mix in, the closer you get to white. So that's ultimately the difference.
Oh, that makes sense. Thanks.
Any other questions?
I have one.
Yeah, go ahead.
So what's that example of ray tracing you've seen which really impressed you, like in a game or movie, some effects?
Surprisingly enough, I know most people when they think of modern CGI, they think of like superhero effects and stuff, the fire, the explosions. But over the summer, I was watching this one YouTuber, and he made a video about applying ray tracing within a pixelated game. And that was really amazing to me because it really demonstrated how this equation is so adaptable over many things. It doesn't have to be for something that's hyper-realistic, has realistic models, real people. It can be applied to even the less detailed things, like those old retro games, in a way that makes those games feel more immersive. And I think that extra layer of depth that being able to simulate life has really accentuates like the retro parts that people really don't talk about, and I think it makes those games even better. And in that sense, I think what makes me so amazed about it is that we can apply it to more than just those those huge budget production movies, but we can do it for even smaller projects as well. So yeah, that's why I was really interested in it. Cool. Any other questions? Go ahead.
Are you referring to Minecraft ray tracing?
Minecraft does apply this, but when I say like a pixelated game, like think Duck Hunt, like back in the day.
Like really
retro
bad.
games. But applying shaders on those games, because those games, you have to remember, are made in 2D and they look like they're 2D. But the moment you add the ray tracing, you add this layer of depth with light. It really makes it more immersive.
The ray tracing can literally make the most ancient looking game appear to be 3D.
Exactly. I thought that was pretty amazing.
Yeah, that is cool.
I can take one final question.
I'm a big fan of video games in the beginning, like 4 years ago.
Go ahead.
I actually did have one more question if nobody else does.
Yeah.
When you were explaining how ray tracing works, it made a lot of sense to me, and I made an assumption that was the magnitude of the ray that was generated was inversely proportional to how bright that pixel would end up being. So if it was like a long
in terms
ray,
of time, right? The one thing about a ray is although it's analogous to a vector in which it has this direction, it doesn't have a magnitude. In this dot product, we just assume that the magnitude is 1, and then we just take the cosine of the angle, and that gives us some value less than 1, and that makes sense, because if you're at an angle, there's a dampening factor, so it should produce less light at an angle than if it was directly on top. So,
so the brightness of the object doesn't have anything to do with how far away it is, it's just based
does
on
not
the
matter.
angle that it is?
It's just the angle. Essentially, it's just the angle, because there's no magnitude to the ray. Right.
next we have Nathan Chan with Professor Jika Turovich and the meaning of words, word vectorization, and the singular value decomposition. Word vectorization is the process of converting language into numbers. Coupled with singular value decomposition allows us to express word vectors in a concise manner.
Thank you. All right, my name is Nathan Chan. Today I'm going to be exploring the meaning of words. So we're going to be understanding how computers understand text, how they understand languages, and then how can we apply this to different stuff in the real world. Okay, so first of all, why do we even want to vectorize numbers in the first place? Well, computers only speak the language of numbers, binary zeros and ones. They can't really understand, hey, how are you, right? So we have to somehow quantify, hey, how are you, into numbers that are meaningful. And so this process is called word vectorizations. And this is the basis for like Google autocomplete. Have you guys gotten really annoyed in typing into your keyboard and they suggest you the wrong word? So that's a reason to try to understand how this process works and how we can improve it. Excellent. Okay, so sorry guys, I'm going to have to go over some definitions first before we get into the fun part. So what is a vector? Well, a vector are objects that have a direction and length in an n-dimensional space. So you can have 2D vectors, you can have 3D vectors. I like to think this as really arrows in the plane. Next slide. Okay, one more definition. What is a matrix? A matrix is a rectangular table of numbers arranged in rows and columns. You can think of this as your run-of-the-mill table, an Excel sheet, stuff like that. So this is a 2 by 3 matrix. Next slide. How do we turn words into numbers? Okay, so here's the fun part. There are many ways to represent words numerically, but we typically like to use vectors and matrices. In the spirit of the World Cup, let's use country names as an example. So Brazil is equal to the vector 15, 8, and 4. So what does this even mean? Okay, 15, 8, and 4 are different components of this vector, and each number stores some information about this word based on certain characteristics. Next slide. Okay, so let's give each country 3 different attributes. Population size, scale from 1 to 100. Gross domestic product, so the strength of the economy, from 1 to 100. Continent, 5 to 35. I know there's 7 continents, but I scaled it up so you can have a more accurate weight. So let's look at this table. So you see Brazil has 15, 8, and 20 for population size, GDP, continent, respectively. You have China, you have Egypt, and so forth. And so you can take a look at each row. So each row represents the country name in some fashion numerically. And these are arbitrary attributes that I've chosen to make it a simple explanation. Of course, if you add more characteristics, it'll be a more accurate representation. Okay, so let's see this graphically. Next slide. Okay, so I'm graphing these vectors on a 3D plane. And as you can see, like Mexico is kind of close to Brazil, you have Pakistan close to India, you have USA and Japan kind of far out there. So this kind of gives you some idea of which country names are closer together, which ones are more similar, and which ones are more distant. Now keep in mind, this is a 3D plane, so depending on your perspective, it's going to change. Next slide. So this is another perspective. You can see India, China, and USA are kind of farther. This could be due to population size and GDP, and the other countries are more closely grouped together. So now, I chose the characteristics, but how do we make this more general? Next slide. Oh, sorry, before I go to that, let's talk about how we can use these vectors. So one application is drawing out similarities between words. So how do we know if Brazil is more similar to Mexico or China? Well, we can use this really nice formula. If you guys notice this is simply a distance formula in 3 dimensions. So because our country names are vectors, we can determine the similarity using this formula. So our vectors are x0, y0, z0 for one word, and x1, y1, z1 for another word. So Brazil and Mexico have a distance of 8, while Brazil and China have a distance of 110.5. And this is pretty intuitive, right? We would expect Brazil and Mexico to be a bit more similar than Brazil and China. Okay, next slide. So instead of arbitrary attributes, can we generalize this process? Because if you think about this, this is just country names. But what happens if we bring in animal names, different verbs, different adjectives? It's hard to choose these characteristics. So we refer to this idea. Words in similar contexts have similar meanings. What does that mean? Okay, for example, I take my dogs to the vet. Okay, I take my cats to the vet. It's the same sentence. I'm just replacing dogs with cats. So they have the same context. And so dogs and cats, we can tell, are kind of similar. This makes sense. So using this idea, we kind of generalize this process of word vectorization. Next slide. Okay, so take the statements. I enjoy math, I like probability, and I like linear algebra, which we can all relate to, right? So let's set our window size to be 1. So what does this mean? So when we're examining a target word, say enjoy, we look at one word to the left of it and one word to the right of it. So for enjoy, I is to the left and math is to the right. And we store the amount of co-occurrences, which is if a word appears within the window size of the target word, into this sort of table here. To represent this in a matrix, next slide, we can create a co-occurrence matrix. So each column is a vector. So probability, you can see it occurs once with like, because I like probability. Algebra occurs once with linear, because linear algebra. Okay, so this is a co-occurrence matrix. Each column or row is a representation of the word. But as you can tell, this is pretty sparse. There's a lot of zeros here. And imagine a document with thousands of words. It's going to be hard to store this. So let's try to simplify things. Next slide. Okay, this is where singular value decomposition comes into play. SVD is a factorization process that allows for us to simplify the matrix we saw before without sacrificing valuable information. So this is a really important formula. This is going to be the main character here. So M is equal to U times sigma times the transpose of V. So guys, pay attention to U. That's going to be our simplified co-occurrence matrix in the following steps. So we take our original matrix, which is M, which was the table of word vectors, and we'll do this fancy factorization process, and we'll get a new co-occurrence matrix called U, and it's going to be a lot simpler to understand in just a minute. All right, next slide. Okay, so before we talk about the math behind it, I want to go through a few definitions. Transpose is simply swap rows and columns. So you can think of this as turning the table on its side. Eigenvalues explains the variance in data. So this tells us how similar words are, how different words are, and so forth. Eigenvectors explains the directions in data. All right, next slide. Okay, so this is kind of complicated. I'm not going to spend too much time on this, but I want you guys to kind of see that there's steps involved in factorizing the matrix M. So we take the M times the transpose of M, and then we determine the eigenvalues and sort them in descending order. If you guys remember, what are eigenvalues? Eigenvalues store the information about the similarity between words. So if we sort them in descending order, the first eigenvalue is going to tell us a lot of information about these words. The second eigenvalue is going to take a little less information, but still good enough information. And as we descend through this structure, we'll get some eigenvalues that don't really tell us a lot. So if they don't really tell us a lot, then why are we even keeping them, right? So through this whole factorization process, we find our new co-occurrence matrix U. Next slide. Okay, so because some of these eigenvalues don't explain a lot of variance, a lot of information in these words, then it doesn't really make sense to keep them because they're not doing a lot of work for us. So this is the story right here. We have our original matrix M, we factor it into U sigma VT, but our main character, if you guys remember U, we can kind of truncate the white space and keep the gray space. So let's look at how this applies to the matrix we calculated before. Next slide. All right, so back to example. When we do this fancy factorizations, this is our U. As you can tell, it's still just as big as our original matrix. So how do we make it smaller? Remember, a lot of these new eigenvalues, or the lower eigenvalues, don't explain a lot of variance. So next slide. So we can truncate it and get a really nice small matrix. So this is after truncation. Okay, if you guys remember, when we're reading this table, each row is a vector. So probability has a vector -0.347, 0, and 0.194. each column is a specific characteristic or attribute to describe each word. So probability has a numerical representation, and math has a numerical representation. Next slide. Okay. So what is the point of this? How do we extract similarities between those two? If you guys remember last time, we used distance formula. We're going to do a less naive approach, something more robust. We use cosine similarity. So this is essentially the dot product formula. A is a word vector, and B is a word vector. And then the cosine theta is what we want to maximize. So if you think of vectors in this three-dimensional space, the closer vectors are together, the smaller the angle is going to be. If you guys remember calculus, because you guys, or linear algebra, because you guys said you love linear algebra, the arrows are going to be really close together, which means our words are more similar, right? So our goal is to maximize cosine theta, because the smaller the angle, the bigger the cosine. So cosine theta ranges from -1 to 1. -1 means that these vectors are kind of polar opposites. 0 is there's no correlation, and 1 is there's perfect correlation. Next slide. Okay, so we've done a lot of work. Let's see how this plays out. So let's take two words, like and enjoy. Like and enjoy are synonyms. So let's plug this into the cosine formula. We get the similarity between like and enjoy is 1. So they're very, very similar. And this is pretty intuitive. The cosine similarity between like and probability is 0. They're not similar. I mean, like has nothing to do with probability. So yeah, this is how we can take sentences, we can store sentences in numerical representations like matrices, and we can compute the similarities between words. So this process is word vectorization and really fundamental to the field of computational linguistics. So why does this process really matter in the real world? So one of the companies the company I work for, Group Solver, you can think of it as a smarter survey monkey. And so we can analyze, when respondents are typing into the surveys, they can type full sentences to describe, hey, how do you like this t-shirt? And they can type into to the survey. But how do you really store their responses in a numerical fashion? This is where word vectorization comes into play. We can store the responses, and we can draw statistics out of it. So then we can tell companies like Adidas, this customer really likes your t-shirts, or this customer really doesn't like your t-shirts. And those are some real world applications of word vectorization. So hopefully this presentation has given you guys an understanding of this whole process. And any questions? Yeah.
Is this also how like machine learning algorithms pick up on like what people are saying and like
Yes,
language and stuff?
this is the basis for a lot of machine learning, a lot of artificial intelligence. There's some smarter ways of doing this. It's kind of a similar approach, but you're right. We can put these through neural networks. Each iteration, we can get kind of more understanding of these texts. So you can take a book, for example, plug it through a machine learning model, then understand what these words are and what the book is saying.
Is there any potential for like outliers, especially if like a word sort of is like a mix of two characters?
Yes. So in machine learning, and in general, the more data we have, the better. So the bigger the sample size, the more accurate it's going to be. As you can see, we only chose 3 sentences. But as you get to bigger and bigger data sets, then things can be more accurate. The more common a word is. So actually, for example, there's like article words like a and the. They don't really tell us a lot about words, so a lot of times we ignore these. If there's a word that we haven't seen before, then we don't have any basis for really understanding it. Because if you remember, the idea is words in similar contexts have similar meanings, so we base it off of contextualization.
So I believe there was like a chatbot that came out like very recently to the public that was super advanced. Cause like you could just ask it a question and it'd come out with like an encyclopedia of information and sort of explain it to you. You think that was made using a process similar to this?
Yeah, so chatbots are based off of, I think, 3 GDP. There's some model right now that's the most prevalent in research. And that model, they use a more advanced process of word vectorization, but they're still computing these words numerically. So if you plug into if you say something in the chatbot, they're able to give you a really kind of human-like response. Yeah.
Go ahead.
Very good talk. I think I understood, but it's not. Maybe I asked this question, you see it right away. I know not much about math. You were saying at the beginning that computer doesn't recognize words; they only recognize 0 and 1s. And look at your vector; they are not 0 and 1s.
Yeah. So you can store these in decimal representations like 1s, 2s, and 3s, and you can convert decimals. Base 10 into base 2, which is binary. So for example, the number, you can have like 0, 1, 0 or 1, 0, 0, 0 to describe these numbers. So basically anything that you can represent numerically in base 10, the numbers we're used to, you can also represent it in binary, 0s and 1s, through a conversion process. So you get to do the question.
Did anyone try to apply this to poetry, like modern
Poetry?
poetry or something?
Yes, they definitely have. I was actually watching a YouTube video. There's a word processor called Lex. I don't know if there's any English professors in the building, but I don't want to give any students wrong ideas, but it can basically generate writing for you, and it's super accurate. So you can plug in like poetry or whatever, and it can fill out the remaining lines based off of the previous words you inputted. So there's a lot of applications.
I have a question.
Yeah.
How are you expecting to see this technology, or what you're showing? How do you expect it to be applied in the future?
Sure. Word processors are one example. I think the mistake that a lot of these companies are doing is they're trying to replace the author with the AI bot. I think it'll be used as an assistant. So it can provide inspiration for what other writing that they can put into their papers. I think there's a lot of ethics involved. How do you correctly credit the author for writing something that they use in an artificial intelligence model? So there's a lot of uncertainty in the future, but I think in 2023 and so forth, we'll see a lot of applications.
Great job. Great job, well done.
Good job.
Alrighty, next we have Ann Kelly with Professor Mentor Giga Perovich, and we are talking about the Eratosthenes seed imprimement classification and exploration of the removal of integers in Eratosthenes seeds and the infinitude of 3 types of prime numbers.
Good luck with that.
Good afternoon, everyone. My name is Ann Kelly, and today I'll be presenting on Eratosthenes sieve and prime classification. Let's begin by getting introduced to the main characters of our story, which are the prime numbers. In order to be a prime number, you need to meet 3 requirements. First, you must be an integer, which is a whole number like -1, 0, 1, 2, etc. Secondly, you have to be greater than 1. So all the negative numbers, along with 0 and 1, don't make the cut. Last but not least, you can't be the product of 2 smaller positive integers. As a consequence, the number 12, for example, could not be prime. 12 equals 3 times 4, and that's a product of 2 smaller positive integers. What you might have noticed with these requirements is, while they make it clear what a prime number is not, they don't tell us a lot about what prime numbers actually look like. Accordingly, it can be difficult to recognize a prime number. That's why Eratosthenes, an ancient mathematician, designed a process for identifying prime numbers. Using the sieve of Eratosthenes, we can find all the prime numbers in an interval starting with 1 and ending with some integer. For example, we could use it to find all the primes between 1 and 100, or even 1 and 1,000,000. But given time constraints, I'll be showing you how it works for the interval from 1 to 30. We begin by listing all of the integers in our interval, and then we cross out 1. Since 1 is not greater than 1, it doesn't meet that requirement to be prime. We circle the closest uncrossed number, which is 2, and that's our first prime number. Now we'll cross out all the multiples of 2, because those numbers can be written as 2 times another number. So they're a product of 2 smaller positive integers. We repeat the process, circling 3, and cross out all of its multiples. Since some of the multiples of 3 were already taken out by 2, we only crossed out 9, 15, 21, and 27. We proceed to 5, and once again, cross out its multiples. This time, we only got rid of 25. And now we're done. Every multiple of 7 in this interval was already eliminated by 2, 3, and 5. So we can circle all the remaining numbers, and we found our primes. While we were going through the process, each prime number removed significantly fewer numbers than the previous prime. 2 eliminated 14 numbers, while 3 only took out 4 numbers, and 5 removed just 1. To investigate that pattern, we'll ask the following questions. First, exactly how many numbers are removed at each step of the algorithm? And second, how many numbers are left behind after each step's completion? To analyze these questions, we'll need some mathematical language. When we want to talk about the prime numbers, we'll refer to them based on their position in the overall list of prime numbers. Here, the first prime number would be P1, the second prime number would be P2, and the 100th prime number we would denote as P100. Additionally, when we would like to discuss the product of the first R primes, where R is just some positive integer we choose, like 3 or 5, we'll use this handy notation, which looks kind of like the side view of a table. The number at the top of that table is telling us when to stop pulling prime numbers from that list. So, for example, if it were 5, that would be telling us that we're taking the first 5 primes from that list and multiplying them together. Additionally, we'll set up the interval we'll be working with. In order to obtain a nice, clean result, we specifically look at the case where our interval ends at the product of the first R primes, where, once again, R is just some positive integer we choose. Now that we have that notation down and we've set up our interval, we can get into the fun of calculating the result. We use approaches from number theory and probability theory, which are 2 fascinating branches of mathematics. Number theory analyzes integers and their properties, while probability theory looks at the likelihood of events occurring. Using those methods, we find the amount removed at the case step and the amount remaining after the case step, for any integer k less than or equal to r. If r were, let's say, 4, that means we could calculate the amount removed and the amount remaining for the first, second, third, and fourth step of the algorithm. To see these results in action, let's consider the example of r equals 7 and k equals 6. When we plug those numbers into our formula, we'll find the number of integers removed by the 6th prime in the interval from 1 to 510,510. And that number ends up being 8,159. So that 6th prime number is being quite efficient. If we plug those same numbers into our second result, we find that the number of integers left behind by the 6th prime in that same interval is 97,926. So there are still many integers hanging out in our sieve. Now we'll turn our attention to those numbers that survive the first k removals. These numbers, unlike the numbers that were crossed out by one of the first k primes, actually have the potential to be a prime number. So we'll refer to them as potentially prime numbers. When we look at them specifically in the interval from the product of the first k primes to the product of the first k plus 1 primes, where k is just some positive integer less than or equal to r, we find that all of these numbers must fit one of 3 forms. The first option for a potentially prime number is to be the product of the first k primes plus 1. In addition, a potentially prime number could be the product of first k primes plus some prime number bigger than all the primes in that product. Last but not least, a potentially prime number can be the product of the first k primes plus a composite number not divisible by any of those first k primes. Here, a composite number is just a number that is a product of 2 smaller positive integers. 6, for example, is a composite number because it equals 2 times 3. Given that these numbers survive the first k eliminations, we would expect them to be more probable to be prime than some random number. But exactly how likely is it that one of these numbers will be prime? Using the prime number theorem, which is a famous result in number theory, we find that the probability of potentially prime number in the interval from the product of the first k primes, product of the first k plus 1 primes, will be a prime number is given by this formula. Basically, if we took all the potentially prime numbers in our interval, wrote them on little slips of paper, and put them in a nice big bowl, this result is telling us how likely it is that we'll draw out a prime number. If we plug k equals 4 into that formula, we find that there is roughly a 54% chance of being prime for potentially prime numbers between the product of the first 4 primes and the product of the first 5 primes. On the other hand, there's only between a 13% chance and a 19% chance of being prime for arbitrary numbers in that same interval. So being a potentially prime number definitely gives you a leg up when it comes to being prime. Another fascinating property of potentially prime numbers is that they include all the prime numbers. In other words, every prime number must also be a potentially prime number. Accordingly, we can classify all the prime numbers according to those 3 forms we identified for the potentially prime numbers. Our first categorization of the prime numbers are Euclidean primes. And those are the primes that are the product of the first k primes plus 1. This type of number was first introduced by Euclid in his famous proof that there are infinitely many prime numbers. There's still an open question in number theory of, are there infinitely many Euclidean primes? In addition, we have the primitive numbers, which are prime numbers that are the product of the first k primes plus a prime number that didn't show up in that product. Finally, we have the partially primitive numbers, which are primes that are the product of the first k primes plus a composite number not divisible by any of those first k primes. Having classified all the primes, we can generalize that initial question of whether or not there are infinitely many Euclidean primes. Now we can ask the question, are there infinitely many primes of each of our three types? Using Bertrand's postulate, we find that there is at least one primitive number or one partially primitive number in each of our intervals. This implies that there are infinitely many primitive numbers or infinitely many partially primitive numbers. However, we still don't know if there are infinitely many of both, or even which of these types will never run out of primes. Based on related research in the field of number theory, we have strong reason to believe that there are infinitely many primitive numbers. R.F. Fortune's conjecture, when interpreted in the context of primitive numbers, says that the first prime number greater than the product of the first k primes is a primitive number. If this were true, it would imply that there are infinitely many primitive numbers. Unfortunately, it has yet to be proven, but mathematicians have gathered substantial evidence for it, so it is quite likely to be true. Additionally, the work of A. Sejchin, M. Krzyk, and L. Sommer gives us that any prime number between the product of the first k primes and the product of the first k primes plus the k plus first prime squared is a primitive number. As a consequence, if we continue to have prime numbers show up in that interval, even if it's extremely infrequently, we would have that there are infinitely many primitive numbers. Our original question of whether or not there are infinitely many primes of each of our three types has yet to be fully answered. That said, we made some advancements on the question, and the fact that it remains an open question reveals part of why math is so beautiful. For every result we derive in mathematics, there are 100 questions we can ask and explore, for mathematics has infinite beauty. These are my references. Any questions?
So what are some of the applications that you were talking about in terms of like, where would you apply some of these computations and connections to?
That's a great question. So my original work, since it was looking at the removal of integers, it gives us at least intuitive feeling of the distribution of primes. Because like I was saying, each prime number is removing fewer integers than the one before it. So even as we're stacking on more and more prime numbers that can be crossing out numbers in our interval, since they're removing fewer and fewer integers overall, we're still going to be having prime numbers show up even as we get into bigger and bigger intervals. Any other questions? Professor Perovich?
And I also like to make a comment. You gave a very nice answer about the internal meaning of what you did, but generally this discipline of number theory was considered for centuries as beauty of mathematics, but just la pour la, like, not many applications. But then since the beginning, since the middle of last century, when we started encryption and coding, then interest in number theory and how to find primes, because you are coding into these primes and breaking the codes, then became a very practical discipline. So now people are very interested in this type of results for the coding.
Any other questions? Yes?
How does this topic overall contribute to your studying and your major?
That is a wonderful question. I actually hope to become a math professor, and part of that will involve doing research. And this project actually helped me identify that I am very passionate about number theory. And so now I hope to continue research in the future in this field. Yes?
Would you be able to touch on some other questions that you want to answer outside of the superconduction?
Sure.
In terms of number theory?
Yeah.
Oh, no, the question was, are there...
Let me come a little closer.
My fault, I'm kind of quiet. Are there any other number theory questions that you're interested in answering?
Oh, yes, definitely. There's actually a very well-known conjecture in number theory called Goldbach's conjecture. And it states that every even integer greater than 2 can be written as a sum of 2 prime numbers. And it's been around for centuries, and yet we still haven't proven it. And so it's one of those conjectures that's keeping me awake at night.
How about perfect numbers? You gave up on that?
I haven't given up on those. No, those are interesting. And another big question in mathematics is whether or not there exists an odd perfect number. So that was actually something I was working on at the beginning of the semester, and I almost did my honors project on that, but then I came across this and I totally fell in love with it. Yes?
Could quantum computers perhaps help solve this issue regarding prime numbers, since they are capable of calculating insanely high values very quickly?
So I do know such computers have been used relating to Goldbach's conjecture to verify it for very large numbers. But in mathematics, even if we knew that it was true for all the numbers up to like 8 million trillion, that doesn't matter. We still need a proof in order to know that it's true for all of the numbers. So while it gives us strong reason to believe something is true, it will never guarantee that it will hold true for all of the numbers. Yes?
So I don't know if you mentioned this already, but is there going to be like a top prime number, or is it just infinite?
So prime numbers, yes. Euclid actually proved that there are infinitely many prime numbers. And so no matter how big we go, we can keep on finding more prime numbers, although they are becoming more infrequent. Alrighty, well, thank you so much.
So we do have a break, but before we go on the break, I want to remind everyone about these QR codes and to fill out the form. So please do that, and then we will go on a 10-minute break. And the presenters' names. First we had Kevin Wu, then Nathan Chan, and then Aaron Kelly.
You can go on your break, though. You're not being held hostage.
Yeah.
But the commentary forms are, so I think the first link on the link tree is the program, and then the second one or the third one is the commentary forms. So there's some more snacks and stuff outside. We also packaged up the wraps, so please feel free to take wraps with you as well. And we'll be back in like 10 minutes. Let's get started at 5 till 3. All that caffeine.
We need to do it, man.
Yeah.
Okay. So next we have Colin Delaney with Professor Linny Chawes on caffeine extraction and study of pharmacological properties resulting from its role as adenosine receptor antagonist. So this is a discussion of the pharmacological properties of caffeine with a focus on the molecular activities due to its structural and similarity to adenosine.
And there's a clicker there for you as well.
Oh, that's great. That's my cue. So, how many of us in here drink coffee or tea? Great, you guys are gonna like this. If not, you'll probably like it too. But so, 85% of the U.S. population consumes at least one caffeinated beverage a day. This makes it one of the most widely used central nervous system stimulants. Concerns still exist about potential adverse health effects of high consumption of caffeine, and I wanted to look into that. Personally, I drink 4 to 5 cups a day, and I was a little concerned. That is the motivation behind my research. So it's very structurally similar to this other molecule called adenosine. So in order to compare the two, I extracted caffeine and analyzed the structure. So here's a little bit of the history of caffeine. First consumed as tea in China as early as 3000 BC. There's cocoa beans that are Mayan. Those go back really far as well. And then coffee in Arabia and northeastern Africa. So they all kind of entered the European market at the same time, which is interesting. And there's honestly like a strong argument to be made that that really powered the Industrial Revolution. You guys all know Isaac Newton. He was a big coffee guy. Voltaire had apparently had 50 to 70 cups of coffee a day. That's crazy. Couldn't be me. So here is the first synthesis of caffeine by M.L. Fisher. If there are any biochemistry or chemistry people in here, you guys already know him very well. He's the guy who came up with the idea of Fisher projections, as well as Fisher esterification. This synthesis here is actually part of his work that got him the Nobel Prize. And then down here I have the biosynthesis in plants. So I created a flowchart here, and you can kind of see what I'm doing. But the idea is by adding an organic solvent, we can take advantage of the solubility of caffeine and extract it. If you look at some of the other stuff here, it's really just, some of these other reagents are just to kind of increase the efficiency of the extraction. I know sodium chloride, it causes the caffeine to be more soluble in the organic layer by increasing the polarity of the aqueous layer. So you heat it and you dry it, and this is what I got in the end. This isn't very good, 63%. Looking around in the literature and online, this whole extraction, no one really gets a good percent recovery using this method. So I'm not quite sure why. There are other methods that you can use they involve more complex machinery, and they're different, and that you can apparently get a little bit better of a percent recovery, but I don't really think it's worth the extra hassle if you just want to drink like Red Bull or something. So here's I hope you guys can see this. When I was looking at it on my computer, it was really hard to see. Here's the proton NMR. So I've drawn it out here, and you can see the peaks, and these represent the different hydrogens here. And I've kind of labeled them here. These numbers, if you guys can see, this is how we know we have the finished product. This is how we identify molecules. And I've also got some more information up there regarding 1,3,7-trimethyl-xanthine. Order that at Starbucks. So yeah, the mean half-life is around 5 hours, ranges from 1.5 to 9. It really depends on the person. It's really different, and there's a whole lot of properties that affect that. As not only the half-life, but some of the other symptoms we'll talk about later. It changes a lot from person to person. So I have this picture here. This is a mode of action. So as all biology students know, ATP is a super important molecule synthesized in cellular respiration. Breaking that phosphate chain creates a lot of energy. That's the energy we use to do cellular work. And then you're left with adenosine when you lose the triphosphate. Adenosine goes into a receptor and it signals your body time to sleep. Caffeine is going to come in and say, no, it's not. And so this is also, it's the most well understood. Caffeine does other things, but that's its most well understood mechanism, and that's the one I'm exploring. You can see adenosine, like, I believe it's right there. It's pretty structurally similar, and that can explain some of this. So there's 4 kind of the adenosine receptors. Really the most, I want to say the most important one for this is the A2A receptors. Antagonism of those A2A receptors is what causes that wakefulness. But there's other stuff. The A1 receptors in the cardiac muscle results in a positive inotropic effect. For those of you, so inotropic factors are factors that increase the force at which your heart contracts. So a positive inotropic effect would in turn increase your blood pressure. So by 5 to 10 millimeters of mercury. Let me put that number into perspective. It's not nothing, but your left ventricle is pumping blood against 120 to 140 millimeters of mercury. So it's not crazy. In fact, a significant increase in blood pressure would be 20 millimeters of mercury. That's what it's considered. So I want to point this out. There are contradictory studies on the risk of cardiovascular disease that relate to this. I was looking back and forth throughout the studies, and this is an active area of research because it has changed a lot throughout the years. Some say yes, some say no. For the most part, though, none of them would hint at any risk of cardiovascular disease at under 5 cups of coffee a day. So that's important to know. So it has a stimulatory action on some of these neurotransmitters. Adenosine typically inhibits neuronal function. So in a way, caffeine is kind of, I don't know the word to use, but that's why there's a stimulatory action. So for any neuroscientists in the room, this is going to be really a gross oversimplification of some. So dopamine, that's like the reward center. Norepinephrine or noradrenaline, that can increase your blood pressure and your heart rate. Acetylcholine is, well, this one's really important. It has a lot of uses, not only in the central nervous system, but in the peripheral circulatory system. It can slow down your heart rate. It's actually, it's really important because without it, your heart rate would actually be faster than what it's supposed to. So you want that. Glutamate is important in learning and memory. So the idea is, while the mechanisms are not fully understood, we can keep track of what these are doing, and this might, in future research, explain some of the symptoms we're seeing with caffeine. These are really interesting to me. This is medicinal chemistry. It's used as a drug. So this first one is in patients with renal cell cancer. The accumulation of adenosine seems to worsen their condition. So adenosine pathway genes are highly expressed. So this study was looking at adenosine receptor antagonists as a treatment for that. Not just caffeine, there are other ones too, but caffeine was one of them. And then the next one is, there are various studies that say it may decrease risk of various types of cancers, and the mechanisms are not fully understood. This one, the one after this is the most interesting to me because, so up to 65% decreased risk of dementia in individuals who drink 3 to 5 cups of coffee a day. To me, that's a crazy number. There's another study about Alzheimer's disease, and it can lower risk for that. They didn't give a milligram range or a cups range. They just said it can lower the range. And then decreasing risk of Parkinson's disease. The maximum strength of protection is at 3 cups a day. So if you drink more than that, it's not necessarily going to be worse, but it's not going to increase the protection much more. Consumption correlates inversely with depression and memory deterioration. They did a study in mice and a human under stress to find this one out. And so I was unable to fit all the side effects on here. You have to think of these things as drugs. And like any drug, there's a long, long list of potential side effects. So some of the most common ones are right here: restlessness, anxiety, and headaches. Those can come just from drinking a cup of coffee, depending on the person. But they will certainly come in the 10 to 20% of people who experience withdrawals from drinking coffee. A thing with the withdrawals is they don't last for more than 3 days, so depends how much you really need to pass your final. Development of a tolerance. This one is, to me, the most annoying because, yeah, for me, I've quite developed a tolerance to this. Your body is going to synthesize more adenosine receptors the more coffee you drink, so or Red Bull or whatever. So to keep up with that, you have to drink more coffee and Red Bull, and this creates a cycle. And I'm still trying to find out where that's going to end with me. All right, so I have my references here. So I wanted to mention. What can I conclude about this now, since the research is changing, and it's changed a lot even in the past 5 years? I think the big takeaway message is to keep an eye on these things. Maybe ask your doctor. It's different for everyone. If I was to put a number on it, 3 to 5 cups a day to decrease risk of neurodegenerative disease. No more than 5 cups a day if you want to be absolutely certain or fairly certain that you're going to be okay, and there will not be any cardiovascular disease. And 50 to 70 cups a day if you want to be Voltaire. But no, I will just continue to watch the research and make my decisions accordingly. Thank you. Questions? Yes.
I want to hear more about that 50 to 70 cups a day.
Me too. I wonder how he did that.
And how big were these cups exactly?
That's a really great question. I don't know.
It depends on the concentration too, right?
Yeah.
Can be a small cup, but very concentrated, like espresso. Like
So is he like drinking gallons of coffee every day?
Well, have you seen those little cups that they give you in the nice fancy coffee shops? It could be. I don't know. I think that's a history question, but
Might have to look into that.
yeah. Yes.
Starbucks invest in research on caffeine?
They should, and they should pay me.
I agree.
I think they do, but a lot on taste.
On taste.
Your slide on the health benefits of caffeine, you said that the research is also mixed on the effects, but are there consistent studies on the positive effects on caffeine as opposed to just the detriment?
In terms of consistency, so some of these references here, I'll try to point them out to you. These are studies conducted in a population, and they're actually, one of them's a little old too. They're actually calling for more studies. They want more definitive data. Of course, to make the claim that it decreases risk of neurodegenerative disease by 65%, you have to back that up. So what they wanted was, they actually asked in their abstract for someone, their conclusions, for someone to follow up on that. So consistent, I don't know. It's fairly consistent, but they want more data.
So I have a question. Oh, sorry. If caffeine is naturally occurring in certain foods, correct? And then you're also creating synthetic versions of caffeine, correct? Have any studies seen positive or negatives based upon whether you're doing like a Red Bull version of caffeine versus a naturally occurring caffeine in, say, a cola nut or yerba mate or something?
That's a good question. I didn't look into the different sources. I did extract it from tea and Red Bull, but I did not examine potential health difference in any of them. But yeah, that's a really great question.
Okay, correct me if I'm wrong, but adenosine is what you said makes us want to go to sleep, right?
Yeah.
And then you said with caffeine, if you develop a tolerance for it because your body generates more adenosine, right? As you drink more coffee, and then it creates the cycle, right? Or am I not?
Not that you're producing more adenosine, that you've synthesized more receptors, so there's more chances for that adenosine.
You won't become more fatigued by drinking or developing a dependence on caffeine, will you? Because you just have more receptors, but the amount of adenosine is the same. Or
No, you should become more fatigued, because if you develop a dependence on coffee, and are you trying to lean off the coffee, or?
I'm just trying to figure out, because I just drink coffee whenever I crave it, which is not that often, but I'm just wondering if I ever do drink a significant amount, if that's going to make me feel more fatigued when I'm off the caffeine versus before I drink.
Yeah, it's going to. These last for 3 days up to that would be one of those withdrawal symptoms. So that lasts from 3 days. I think at largest up to a week. You should be okay, but yeah, you will feel more fatigued if you just decide to lean off of coffee. I've tried too, so there's personal experiment there.
Piggybacking off Kevin's question, do the receptors deteriorate? Do they disappear over time if you're not drinking a lot of coffee? Because you're synthesizing more receptors, but does it revert back to this equilibrium state?
I'm not sure. I'm inclined to say that since the restlessness, not the restlessness, the being tired overly, that was one of those withdrawal symptoms, and it is supposed to go away from between 3 and 7 days, mostly 3. I don't know if that's because the receptors are deteriorating. So yeah, that's a good question.
Thank you so much.
Yeah, I can.
Yeah. Thank you. Okay, as somebody who drinks a lot of this zombie juice, is there a way to build tolerance, or do I just have to go off of it for a while and drink it again?
To build tolerance.
If I'm used to it right now, do I have to go without it for a little bit?
Oh yeah, that's actually something with a lot of these stimulants, only caffeine. But yeah, you would have to wait. That's how a lot of the drugs work. You would have to wait a little while, and then that first cup after a week would be more of a kick. If that's what you were asking. Yeah.
So next we have Clayton Doyle and Professor Lynn E. Miller. Clayton will be discussing attention deficit hyperactivity disorder and evolutionary and social advantage. Research into ADHD has demonstrated clear neurobiological causes. This condition exists because it offered our ancestors selective advantage and may still be advantageous today.
I'm going to first ask a question. How many of you know someone with ADHD or have it yourselves? Just raise your hand. Okay, fair amount. ADHD actually can be an advantage. I know it seems odd, it's portrayed as such a detrimental thing, but it can be advantageous, and I'll tell you why. ADHD is supported by various biological processes, and these symptoms that are created by ADHD are helpful to our prehistoric ancestors and actually have a positive value in today's society. What is ADHD? ADHD at its core is a learning disability. This learning disability greatly affects someone's life throughout their entire, sorry, I'm stumbling a little bit. It greatly affects someone's life, their whole entire life, most of the time. I'll get into that a little bit more. There are 3 main behavioral symptoms involved with ADHD, and those are inattention, impulsiveness, and hyperactivity. And these symptoms can actually manifest differently on a person-to-person basis. Some people might be more hyperactive, some people might be more impulsive. It really depends on the person and the setting. And these symptoms can be further broken down into various subcategories, as I'll show you right now. These are very common ways that ADHD can be manifest. Failing to pay attention to details, not listening when spoken to, difficulty focusing on the present, excess talking, restlessness and excess energy, interrupting others, and impulsive decision making are just very common ways that these behaviors can manifest. How is ADHD diagnosed and measured? Most people use the Diagnostic Statistical Manual of Mental Disorders, the 4th edition specifically. And in order to qualify for a diagnosis, you have to show 6 of the main behaviors of ADHD over a 10-week period. And those behaviors have to be present in your early childhood years as well. In addition to that, those behaviors must affect multiple settings of your life, whether that's academic, career, or social, and impact them in some sort of negative way in order to qualify. And in addition, those symptoms can't be explained by any other mental disorder or illness. Diagnosis rate. Funny thing about that, it used to be around 5% in 1996 worldwide, but now in the US it's around 9%. It's actually been going up over the years. This is the National Health Interview Survey, a study done in, or a survey done in America, and we just pull and ask who's been diagnosed, who's not been diagnosed. But as we see, it's been going up. Professionals aren't sure why it's going up. Some believe it's because there's actually more people with ADHD. Others believe that it just has gotten really good at recognizing it. We don't really know now, only time will tell. If the graph flattens out, we know we've gotten really good at recognizing it, but if it keeps going up and up and up over the years, there are more people with ADHD. Too early to tell that right now. All right, ADHD throughout the lifespan. ADHD is most often diagnosed in childhood. That is when most people are diagnosed, and this is when you start to see those key behavioral symptoms in the form of behavioral disruptions. These occur in most settings whenever there's an outburst of one of the symptoms that negatively impacts the situation this person's in. This often leads to troubles with academic life. For instance, children might fall behind on their work because they're unable to pay attention, or they might ruin friendships by blurting something out they were thinking but couldn't really filter it out before it got to their mouth. And in addition to greatly affecting academic life, this is when it can actually affect the family. Unfortunately, there are some families who refuse to acknowledge mental illness or mental disorders, and this can greatly impact the child. Children can feel unsupported and unwanted, and like they're doing something wrong despite them, just trying to get by. Moving on to adolescence, though, there's an increased risk of drug and alcohol abuse now, and antisocial behavior. This is because low self-esteem is often associated with ADHD. I'll get into why in a little bit. But those are the only main new symptoms besides the 3 core behaviors. And finally, adulthood. 2 out of the 3 people that are diagnosed with ADHD will continue to have it into adulthood. That is the majority. Most people who have ADHD will continue to have it throughout their life. It's not really a curable disease. That's not how it works. And this is when you start to see ADHD start to affect one's motivation. So people might fail to do basic, life skills like chores. They're not motivated to do that. And this is where you see people drop out of college or quit their jobs and just stagnate with their lives, unfortunately. But that is one of the major shifts at this period. Going into the biological causes, though, ADHD is largely caused by biology from our current understanding of it. And first, when we're talking about brain structures, for any biologist, by the way, I am an anthro major, so just bear with me, I guess. This is the prefrontal cortex, or the PFC. It regulates attention, impulse control, emotion, and cognitive decision making and planning actions. What are planning actions and cognitive thinking? It's basically what your brain does in response to things. Think of you having a conversation with someone, and you're thinking one thing, but you don't say that out loud. That falls under the impulse control, and you're planning ahead to say something or act in a certain way. Through fMRI scans and other brain imaging software and technology, we see weaker activation in people with ADHD. Their prefrontal cortex does not show as much signals or electrical stimulus happening in the brain, which shows that there's something going on there. Going further into that though, we're going to start talking about neurotransmitters. The main neurotransmitter talked about when talking about ADHD is dopamine. Dopamine specifically affects feelings of well-being and regulates the reward system as well as just other functions in the prefrontal cortex. People with ADHD tend, not always, but tend to have low dopamine in their brain. Whether it's because they're not activating their receptors as well as others, or they actually have much lower quantities. It really depends on from a person-to-person basis, but the general consensus is there's just not enough dopamine activation or actively, being transmitted in the brain. Long pauses in stimuli lead to people with ADHD not paying attention. What does that mean? Well, say someone is talking really slow and very monotonously. People lose focus because the reward system actually not only rewards your brain for when it's doing something you like shopping or watching your favorite movie or whatever, it also placates the brain. Basically, it tricks the brain into actively doing something that's good for it and maintain behaviors. So if you're focusing on a subject that maybe you're not particularly interested in, but you have to take the class for, get that general ed credit, whatever, you have to pay attention, right? You have to take notes, and most people can do that just fine. You might not be enthralled with whatever, but you can still pay attention. Well, that's because dopamine is circulating through your brain, so you feel good, and not necessarily amazing, but you're feeling better, and your brain is being tricked into thinking this is a positive action. I'm going to keep doing what I'm doing. Obviously, there's not enough dopamine, brain's not really doing that well. Dopamine receptors. This is where a lot of research has gone into. There are two main families of dopamine receptors. The D1 family of receptors, which includes D1 and D5, decrease noise. Noise is basically everything in your environment. So say you're trying to, again, go back to the lecture example, listen to a teacher talk. Well, if you're picking up everything in the room and trying to tone all of that out just to focus on one thing, that's decreasing noise. Another example is you're in a very loud room with many people having conversations, and you're just trying to listen to the person right in front of you. Just ignoring all those conversations, that's decreasing noise. But with ADHD, it's a lot harder than that. Their D1 and D5 receptors aren't activating as much. So they are unable to filter out all of this extra stimulus going on in the environment, and they're jumping around and can't zone in on what is important and what is not, even if they're trying sometimes. The second family of receptors, the D2 receptors. This is D2, D3, and D4. And this regulates response firing as well as sustained attention tasks in the prefrontal cortex. Response firing is again, responding to some sort of stimulus through impulse control or other reward-like behaviors, or and sustained focus tasks or continual performance tasks are doing something over a long period of time. And so writing for hours and hours and hours, doing a project like this or something, that is a continuous performance task. And so people with ADHD tend to just lose this interest in what they're doing and move on. In addition, there are high theta but low beta waves circulating through the brain in people with ADHD, and this is found out through, again, more brain imaging technology. And theta waves are responsible for relaxation. Relaxation of the brain, while it can be attributed to sleepiness and tired, it can also be attributed to just the brain relaxing and not performing as well as it should. Beta waves, shockingly, stimulate attention. So if there's not enough beta waves or low activity of beta waves, or they're weaker, you're not going to be paying attention as well. But moving on to DNA. ADHD is highly dependent on genetics. In fact, there's a 74% heritability rate for ADHD. This means that it is very, very influenced by various generations of people, and it's highly passed down. We know this from a meta-analysis of over 37 studies of identical twins and fraternal twins. And as you can see, these are all the studies, and it was basically you compare the two twins, and most likely, if one twin has it, the other twin also has ADHD. More studies found that there's a 20 to 30% chance of someone with ADHD having a sibling with ADHD, and one half of parents with ADHD will have a child with it as well. The thing about DNA, though, is that through genome-wide association studies where they compare two genomes, or not two genomes, a bunch of different people's genomes, which is their whole entire genetic code, it was found that there was no major gene variation, meaning there wasn't one gene that contributed a massive effect to ADHD. It also was found that it's different in every one. There's not one, all the subjects of this study, they didn't have a lot of overlap in their genomes, and so that meant that there's many smaller variations to DNA that are different from person to person, so it's not easily measured or tracked, and it all adds up to the whole of ADHD. There are some genes, though, that are specifically looked at. DRD4 codes for dopamine receptors, specifically the D4 receptor, and it leads to difficulty in continuous performance tasks. And this gene, that's the variation common with people that have ADHD, make the receptors less sensitive. They're not activating as much. So yeah, that's kind of just basic, very basic biological overview of ADHD. Moving on to the evolutionary benefits. There are two main theories. The first theory is how it would have been beneficial to hunters in our prehistoric time. ADHD has, some different behavioral symptoms, and the first major behavioral symptom that's potentially positive. Again, this theory is a little more loose. Bear with me. Hyperfixation, which is very common with people who have ADHD. They have an interest, they are very interested in it, and they become focused in it, and they become very obsessed with that. This would have meant that it would have immersed hunters within the hunt. Hunters could have become very excited, and hunting would have become their life. They would have become very good at it, and this could have given them a leg up against other people that they were competing against. The next one is impulsivity and fight or flight responses. So we know that the prefrontal cortex regulates your responses to actions. We'll say a lion jumps out of the bush and is attacking you. Having to think of, okay, I'm going to move out of the way, or I'm going to do this, I'm going to do that, trying to come up with a response to this takes time. Wouldn't you rather just act? I mean, you might not act correctly, but it's still better than not acting at all. And finally, distractibility equals alertness. A little weird, but when there's all that noise in the environment, it's very difficult to lose track of things. You're being exposed to all of the noise. You're much more likely to see something move by you. Since you can't filter out, you can't focus in. But moving on to a theory that has a little bit more of data behind it is the fact that it actually can increase maternal attention. Monkeys and apes, their children cling to their hair, and they're carried everywhere. This ensures they're protected, they're well nourished, and they are always by their mother's side. Humans don't really do that. We might carry our babies around, but they're not with us always. And so there was a study done where it looked at unmedicated ADHD children and control subjects, and it was found that kids with ADHD got more maternal contact and interactions with their mothers. Basically, louder, obnoxious kids get more attention, therefore they get what they want. And this could have meant that they were much more likely to survive through adulthood and other various benefits, such as better nourishment and other things like that. But moving on to the modern benefits, there is one main modern benefit, and that is it's maybe beneficial to entrepreneurs. One study looked at how ADHD promotes risk-taking and how that could be beneficial to startup companies. They looked at MBA alumni from the top 50 business schools and found that 34% were involved in startup project, 14% were diagnosed with ADHD, and that a majority of these subjects thought that in heightened risk-taking behaviors helps make their startup lift off the ground. Since you have to put yourself up there, you have to throw a band into the wind and just go for it. So many people thought that was beneficial. In conclusion, ADHD is caused by various biological factors that lead to the behavioral symptoms of inattention, impulsiveness, and hyperactivity. We see that dopamine allows for the prefrontal cortex to function. In ADHD patients often have a deficit of dopamine. ADHD has a clear genetic background and foundation, including many small variations, as seen with the genome-wide association studies, the twin studies. ADHD is beneficial to our ancestors as it may have allowed them to be better hunters or get more maternal contact. And finally, it can be helpful in an entrepreneurial setting in the modern day. And the significance of all this is that there are more people than ever who have ADHD, as there's more people being diagnosed, and it is a lifelong it's a lifelong being you have to deal with. And so understanding the biological causes and the social consequences of ADHD is super important, as it may allow for further research and people to find how to channel their disability or learning disorder into something positive. So yeah, that's my presentation.
So you said you were an anthropology major, so I was interested if you would want to take this research topic and do some sort of behavioral study, and if you would, what kind of demographic would you want to study, or what kind of behavior?
That is a really good question. I would actually want to look at probably teens. So I don't, you guys probably can tell, I have ADHD. This is a very important subject to me. My brother has ADHD, my dad, not diagnosed, probably has ADHD. He should be diagnosed anyways. That's besides the point. So I would love to look at teenagers, as this is, being a teenager sucks most of the time, right? And so having an extra layer of problems with ADHD is really rough, and I would love to see how teens could channel this into something positive, and how they could, if they learned about, if they could channel it into something positive, what they would do with that. So yeah.
Yeah, sort of kind of wanted to talk about that. I know when I talk to my friends about ADHD, because along with our majors, one of the things that comes up is that, referring back to when you're talking about when you diagnose someone with ADHD, the actual requirements seem quite arbitrary.
Yes.
And I think they also seem to cause more false positives, at least with like after we introduce technology, because just naturally our attention span is much shorter because everything's so accessible and fast.
Yes.
And just as like the younger generations, we become more inattentive. So do you think with like technology, do you think the increasing diagnoses with ADHD stems from like just outside factors as well, other than biological?
So I didn't look into necessarily false diagnosis rates of ADHD. I read a little bit about it. It was ADHD is the most and the least falsely diagnosed mental disorder, believe it or not. Yes, there are people who will diagnose their 5-year-old because he's being hyper as a 5-year-old with ADHD when, I mean, maybe not. But then there are also a ton of people who have it and are just not diagnosed. And so, yes, I absolutely do think the fact that our attention spans have, I think the average attention, I could be wrong on this, is 3 seconds. If you don't have their attention in 3 seconds, you're done. So I definitely think that does have an effect, and it could lead to false negatives, but also could just make people with ADHD, make ADHD actually more common potentially.
I have kind of a two-part
Go
question,
for
or
it.
two questions. One is that information about the dopamine levels was fascinating to me. And so
Yes.
I guess the first part of my question is there a correlation between ADHD and depression, especially among teenagers? And then also, did you do any research on medication and seeing ADHD as, a positive, right? If we're seeing it as something that we developed, evolutionarily to survive for humanity, what's your perspective on, using medication for those with ADHD versus?
Of course. So yes, absolutely, there is a link with depression and ADHD. Dopamine regulates feelings of well-being, and so if there's not enough of it in your body, you get that low self-esteem. And unfortunately, that's just how it is. And we were at an all-time high of depression rates after COVID and all that, so not great. And to answer the second part of the question, I think medication, if done correctly, is great. Because everyone with ADHD has a different form of it, basically, you need to find what works for you. Often ADHD medication targets a neurotransmitter mentioned in the coffee presentation. I'm going to butcher its name. Norepinephrine? Thank you. That one. I've tried saying it 100 times. I've not gotten it. But yeah, the medication often targets that instead of dopamine because if you have constant dopamine highs, that's not great for you. As instead of regulating attention and focusing on something, everything is rewarding you. So you're just like, okay, I'm existing and my brain is happy. not great for you. But yeah, I think if you find a medication that works for you, that's awesome. Again, I've had ADHD, and I know people who had ADHD. I was put on Adderall at in 4th grade. I was pacing back and forth in the backyard like a polar bear, like a caged animal. It was real bad. But again, you have to find what works for you. And so I think it's fine. And I think once people unlock that genetic element and figure out how people can be diagnosed genetically, you can find what actually works best for you. One more question? Or?
Yeah.
Okay.
As a student who also has the ADHD, have you found a classroom environment here at Costa or someplace in high school where you're like, wow, this instructor, the way they teach, just works well for learning that?
She's actually in the room. Yeah, she's...
I paid him to ask that question.
Okay. That makes a lot of sense. No, she is super high energy, and so it is impossible not to pay attention. Since if you don't pay attention, you are going to miss maybe a textbook worth of information. And so very high energy classrooms, and especially, again, that hyperfixation thing. If you find something that you love, you're going to pay attention. That's just how it works. And so high energy and something you like, you'll pay attention. It'll be great. That's what I found. I think that's it. All right. Thank you, guys.
Alrighty, so next we have Colin McDonald with Professor Robert Bond, and he will be presenting beans, maize, and the cocoa in the Aztec diet, culture, and religion. This is an examination of the cultural and religious significance of beans, maize, and cocoa in the Aztec Empire.
Hey, so you guys may be wondering what the importance of these may have been. Maize was, for the most part, just the centerpiece, the center food that the Aztec Empire kind of revolved around. It was used basically in everything, and culturally you can see it in any Aztec imagery for the most part. Beans mostly served as a source of nutritional value, also supplementing for the shortcomings that maize had, mostly in terms of protein, while cocoa was a form of currency that went alongside cotton as just the main source of trade for the most part. Speaking of which, cocoa was more if you were to compare it to modern money, you could consider it like quarters or cents, since the super valuable stuff was this fine cotton, because I know in one place it was equivalent to something like 400 plus hours of labor, so this was super valuable stuff. So cocoa beans were, speaking of which, they aren't really beans in the traditional sense, they're more like seeds of sorts. So you don't, well, they may have the word bean in the name, they aren't really as such, so I just refer to them as cocoa to avoid confusion. In cultural traditions, they were often used as an essential part of festive drinks. Sometimes you would heat them up, sometimes they'd be cold. There are also traditions around collecting them in certain months. I know people would really make a big deal out of collecting this food for different uses, but mostly it was eaten and used by the most elite parts of Aztec society. Yeah, as a food, it was used as a spice sometimes. Often it could be just eaten raw. I know a lot of it was collected in coca houses for soldiers to consume. And speaking of the currency a bit earlier, it's really interesting because we wouldn't associate food as a form of currency while also serving in some of these foods like mole. Today, people say a lot about you're burning money, but these guys would literally eat it. So there's often a lot of stuff about that. It was mixed with all sorts of different foods that are also mentioned, beans, spices, chili peppers, all that sort of thing. So cocoa was really used in many ways, but it was mostly a delicacy. While accessible to the public, that was mostly due to slave labor. But yeah, it was mostly just something the elite used. Beans, on the other hand, quite popular, pretty commonplace. They originated in the region. They were around, but their importance really was exacerbated during around 8,000 BC, a long time ago, because the region became a lot warmer, so other plants like squash, amaranth, corn, and beans, all these became very important for feeding the population. This is likely even more so because hunting and gathering was really difficult. This might have also been due to the, again, increased temperatures and just the fact that hunting and gathering is simply not as reliable as just growing a food like beans, which have excellent nutritional importance. They serve, as I said earlier, the basis alongside maize as an important diet that they were often mixed with herbs, all that stuff to just make the basis alongside maize to make essential parts of what people ate. So in this respect, beans were essential for the survival of the Aztec empires. Without them, it is debatable whether they even could have existed because of how important they were as a source of protein. The only other thing they really could use in this respect were eating bugs, which are still seen today as a source of food, but really beans are a far more reliable method of gaining these important nutrients. In Aztec culture, they were, alongside maize, an important part of foods that were eaten among them. Among cotton, mole, they were very commonplace in a bunch of dishes. I believe that pozole here. There was often cultural traditions around collecting these fish fruits, I believe they were called. This ritual around their collection during certain times of the year. The Aztecs did really value the food they ate, and really their whole culture was revolved around this aspect, and foods like beans were really an exception. Yeah, sometimes they were involved in ceremony, as mentioned earlier, with the Izwai. I don't know how to pronounce that. Let me know if anyone of you can. But yeah, they mostly would braise beans and maize. It was used in a lot of rituals, since beans and maize were kind of intertwined. And since maize was so important to Aztec rituals, beans by proxy would also be involved in these. Speaking of the elephant in the room, tradition around the beads collection, as mentioned earlier, they would generally just be used and collected in various forms. They also had some symbolism around a circle of life, since the regrowth of beans would often, around winter and spring, would have a lot of symbolic value to the Aztecs. Grounding beans, all of that really helped connect the Aztecs to their gods in many ways. And in many ways was a force of life. Maize really was the main food here. It was eaten in basically any form you can think of. I did not even know how many ways it was used. It was used in cakes, it was used in drinks, like it literally would be used in basically anything. Tamales, beef, ground maize, made porridge. Basically anything Aztecs ate, you would have corn in this. There isn't really a food in the modern day that has even remotely close to this equivalence. Atol, as we can see, the process of making it was fairly difficult, but they did it nonetheless. Maize was deeply connected to the gods in a circle of life, you could say, where humans would eat the maize, which would feed them. And this is how it relates to the main thing you think of when you hear the word Aztec, cannibalism and ritual sacrifices. So the idea was that through this type of thing, you would be feeding the gods that would then basically keep the sun in place, which, as we all know, directly allows maize to grow, which is this circle of life involving ritual sacrifice. And so as a cultural food, this was very much the core piece. Now, Aztec culture obviously did revolve around most foods, but visually, in pretty much every tradition, maize was the key food, which structured the relationship between, us and the gods above. Cannibalism is directly related to maize. People who still speak the Aztec language will sometimes assert that corn is quite literally in their blood. So in a way, you weren't just eating people during cannibalism, but you were also eating corn. Although it is important to mention that there are a lot of misconceptions around cannibalism in the Aztec Empire. They wouldn't just pick someone off the street randomly. Sometimes they might do that, but usually they wouldn't just pick you up and throw you in the pot or something. Usually it was slaves, as you'd expect, or some supernatural form of selection, like cowlicks. How that relates to it, I'm not exactly sure. Yeah, so really maize was really important in these rituals of cannibalism. They are like so directly connected. Humans essentially in their culture were made of the stuff, which they kind of were, given it was one of the only things they ate, alongside the other foods mentioned. Yeah, so such an essential part. So generally, when you look at the Aztec culture, you can't really go anywhere without looking at this particular food at all. Like, there are literally gods dedicated to this particular food. When you look at the different impact of all these foods individually, they can be seen as essential for how the Aztec Empire thrived through history. The Mayans, the Inca, had some similar reliance on these foods. But what I want to look at when looking through all this is how we can apply this to the modern world. What foods are essential for cultures and civilizations to thrive? And I would say you shouldn't just look at the nutritional values of every food, but also you should think about how it will culturally impact every individual in the society, as emotional well-being is often a core characteristic of the most successful civilizations throughout history. And I hope with this knowledge we can really help develop the rest of the world and allow everyone to reach their full potential. I had a lot of sources, as you can see. Really was a pain to cite these, as you may imagine. Any questions you guys may have? Yes?
Why particularly the Aztecs? Why did you choose them? There are so many interesting cultures, and Aztecs are definitely one of them, but why did you choose them?
So I actually started this this whole project I went on looking at beans because I was like, hey, I eat Mexican food a lot. I think they're cool. Quite literally, that was the reason. So I looked into how the beans I liked were used, and the Aztecs to me looked really interesting for a variety of the reasons mentioned. And then I decided to, after looking more into that, include some other foods like corn and cocoa, because they also had various interesting roles in that society.
Thank you.
Yes?
So I know you mentioned corn, bean, and cocoa. Was rice in their Aztec culture? I'm just curious, because I see a lot of rice in a lot of foods today. It's really prevalent.
I assume there was at least some form of rice, but I did not find it in a lot of these foods that I looked at. Rice wasn't really as culturally significant as those three. Yes?
In the context of beans, you mentioned a ceremony called poamu. Can you tell us anything more about poamu?
Yeah, usually as a ritual, it was just based around its collection. And also just kind of holding it up. Yes?
I had a question. You caught my curiosity when you mentioned that cocoa beans are used as a kind of as a source of trading. As an economics major, I'm curious as to how something that can basically be farmed be used as like a source of or a medium of exchange. I'm wondering if you know anything about like how cocoa was controlled or how.
I guess I should have gotten to that in this, but generally they were, for the most part, just the elites. Like, they would mostly control it. A lot of it would be planted into cocoa houses that would be like their soldiers. And occasionally it would be available to the public just because the elites had too much of it to use it because they had slaves producing most of it. So mostly it was an economic situation where the elites controlled like a vast majority of the wealth, and most normal people only had it as like occasional ceremonial food to consume. Yeah.
What aspect of the food products did you find most interesting? The cultural aspect, the religious?
I mean, to be honest, like many of you probably, I did find the connection between maize and cannibalism to be particularly interesting, as I had never anticipated there being that much of a reason behind such a vicious act as to have a whole system of gods and food worship behind that. So yeah, that particularly surprised me. It was quite interesting to me, as you may expect. Any other? Oh, yeah.
So that was a really nice talk. Thank you. I enjoyed looking at the pictures. So you mentioned when you talk about beans, you're talking about the protein, providing protein sources to the as a tech. So is that a modern interpretation? I would assume we think that's what happened, right?
Yeah. I mean, you can't really in history literally go back in time and see that sort of thing, but it is quite likely that beans were used to supplement the shortcomings of maize, since it provided a lot of crucial nutrients that maize lacked in many ways.
Okay, so I think that answers my question, because I was wondering when you go into the literature, any mention from historical references indicating this is some essential food source.
I mean, I'm not quite aware of if I highly doubt they knew about the specific proteins in these different foods, but likely they just used it alongside maize because it was good for them, and they would notice that it felt good. I'm not too sure how food selection worked too much at that time. I could do more research on how cultures decide on which foods are significant, as I do wonder what about maize specifically made it so appealing to basically make a whole culture devoted to it. Oh.
Okay, so before we wrap it up, I just want to remind you to fill out that feedback forms. We had Colin Delaney for the caffeine, Clayton Doyle for ADHD, and Colin McDonald for the Aztecs. Thank you.
Yeah, I think that's it. Feel free to hang out. Chris, do you have any other announcements?
Yeah, remember, again, if you're interested, proposals for your project. The Irvine Conference does have posters as well as oral projects. And if you're selected, we'll professionally print your posters to bring to Irvine. So that's something that if you're interested, please come and talk to me. Remember that OMNI extends to tomorrow as well. We have a morning session at the CLC starting at 9 o'clock. So why don't you come by and visit us. We'll be spending the morning over at the CLC. And don't forget, there's also another OMNI in the spring. And so again, I want to say thank you to all the students and faculty that support us. So it's just been a great day. It's been a full day. But again, safe travels home, everyone. Thank you.
Thank you.
I actually have my graph here.